Okay, so thank you very much for the invitation, and also welcome everyone to One World Seminar. So it's a good way not to travel too much. Okay, so there's a representer theorem in the title. You all know what's machine learning and inverse problems. And so representer theorem really refers to a way of actually representing the solution of sort of optimization problems. Oops. Okay, so now to set the stage, we have like the variational formulation of inverse problems, which is sort of the standard way of formulating this kind of problem mathematically. So you have some unknown object that's seen through an integral operator, a microscope, an MRI. You have sources of noise. This produces blurring. And then the problem is, given those measurements, which are usually discrete, how can we recover here the unknown concentration of fluorophores in 3D? And so the usual way then is to state that as an optimization problem. And what you're doing, you are sort of enforcing a consistency between, let's say, your reconstruction here, simulated measurements of your reconstruction compared to your measurements Y. And of course, because the problem is usually ill-posed, you're also like imposing some regularization, like, for example, putting a penalty on the L1 or L2 norm of some operator applied to your signal. Okay, so that's inverse problems, but in fact, learning, there was machine learning in the title, is also a linear inverse problem, but an infinite dimensional one. And so here the situation is similar. So you're giving like a series of data points. So X are some data points, and maybe Y should be some outcome that you associate to a given pattern here. Now you want to find a function that goes from Rn to R, so such that the function applied to your data point gives you your predictor here, Ym. And again, this is a ill-posed problem in principle. And so early on, people have reformulated that using regularization theory. And so again, here you are introducing energy function, for example, L2 norm of some operator like the Laplacian applied to your function f. And you're trying here to solve then this data consistency constraint here, that you want your Y to be, I mean the f of x here at the data points be relatively close to your Yn. And then here you are minimizing here this regularization term here. And this you can also reframe in terms of linear least squares, like least square fit, where using Lagrange multipliers, and have this kind of problem. And now if you solve that kind of problem, remarkably, using the theory of reproducing Kernel Hilbert spaces, you can find that the solution is a kernel estimator. And this is very much the foundation of all classical machine learning. And here is this famous representer theorem for machine learning. And what does it tell us? It tells us actually that the minimizer of that over a certain Hilbert space H. And now I remind you, this is an infinite dimensional problem because f is just a function in a certain Hilbert space. And so the representer theorem tells us that the solution of that problem, rather remarkably, is a linear combination of kernels. Okay, so those kernels are those guys RH, that depends here on X, which is the free variable, and XM here is the location of your data points. And now what is this RH? This is the so-called reproducing kernel of a reproducing Kernel Hilbert space. And such spaces are actually characterized in the sense that they exist a single kernel with something that goes from RD to RD into R. So X being in RD. And so it is a kernel that if you fix one of the variable, this thing lies in the Hilbert space. And the other thing is the reproducing property, that if you now fix at that particular location and leave this variable open and make the inner product with a function f, that this will sample the function at x0. So it's like, it's acting like a Dirac. And in fact, there's a formal characterization that uses the Riesz map, that actually this reproducing kernel here is, in fact, the Riesz conjugate of Dirac located at position x0. And so it's a unique guy here of that form, and that then gives this representation in terms of kernels. And this is very old. It goes back to Debord. Actually, you were asking me about splines. In fact, it's the spline guys who found those representation first, and then it was carried over to machine learning. Now you can be more general. Instead of doing a quadratic error term, you can in fact put any convex cost function here, and you find exactly the same kind of solution, except now that your problem has to be solved iteratively. But the good news here, and this is where you have the representative theorem, actually this is a sort of miracle. It tells you that the solution of this infinite dimensional problem lies in an m-dimensional space that is actually spanned by those reproducing kernels. So then, while you do the learning, you just have to find those coefficients, so m coefficients, you know, the number that you have data points. And this is really like, supports the theory of support vector machines, kernel methods in classical machine learning. Okay, now, in this talk, actually, what I'm asking myself, is there a mother or a father, call it the way you want, of all representative theorems? Because we saw that we had a kind of consistency term, we had the regularization, and the classical representative theorem, we're saying, okay, we are lying in some Hilbert space. When you're doing machine learning, the measurements you're taking are just point functionals. So evaluation of your functions at the location of the data points. And of course, there's already Shulkov, very famous theorem, where here, if you put an arbitrary convex data term, it still works. But we want to look at a more general setup so that X can be a Banach space, that those functionals that are acting on the F that you're trying to estimate, they can be arbitrarily linear functionals. I mean, this guy already said can be an arbitrary proper convex loss function. And then you can also have a function psi here that is an arbitrary strictly increasing convex function. Okay, so that brings me now to the content of my presentation. So I just gave you the introduction here. So I want to tell you about the mother of all representative theorem, at least some of them. Maybe Vincent will have some more. And I'll talk about applications, optimization in specific Banach spaces. And also, like, interestingly, I end up with a connection to deep neural networks. So that shows you that this mathematics is not only relevant for old style, you would say classical machine learning, but also modern machine learning using deep neural networks. Okay, so I mean, my talk really revolves around the general notion of Banach space. So I think you're a mathematician, you all know what's a Banach space. So a Banach space is a vector space equipped with a norm. And what's important with the Banach space is actually that it's a complete norm space, okay? So that if you have a sequence that is converging to a certain limit in the norm, then that the limit of that sequence also be part of the Banach space. Now, the fantastic thing with Banach spaces, it's really general. So the simplest case is just if you are an Rn, so finite dimensions, but you can also have spaces of functions, and so that's more what we're looking at in machine learning. But you can also have spaces of vector valued functions. So here we're going from Rd to Rn, and so that's also very relevant to machine learning. But you can be much more general. You can have spaces of linear functions going from the Banach space into R. And if you want really to be completely general, you can have a linear space of bounded operators, linear operators going from one Banach space to another Banach space, like Rn here being a special case of the Banach space. So it's amazingly general, this whole framework. Now, if you have a dual Banach space, there's also the notion of a dual of a Banach space. So formally or at an abstract level, this is just the space of all continuous linear functionals that are acting on the Banach space. So you can either write it like that as a linear functional acting on a member of a Banach space, but we prefer to indicate it here with the duality product here. And so this will give you just a number associated to every member here, f of your Banach space, but this is being continuous. And then the dual of a Banach space is equipped with the dual norm. And so this is just, if you look in the book on Banach space, it's very standard. So it's just the supremum here over the duality product, but here divided by the norm of f, and which you can also write in this way here. Okay, so that a supremum over the duality product, but with the constraint that the norm of f is 1. Now, there's a generic duality bound, and I like to see that as the extension of the Cauchy-Schwarz inequality. And if you look at the definition of the dual norm, it's really very straightforward, because I mean, this is the supremum, and so the supremum is obviously greater than the not supremum, okay, just every guy. And then when you move this guy up here, you have this duality bound, okay? And now, maybe to be a little more concrete, for example, if you have LP spaces, it's well known that the duals of LP spaces are LP prime spaces, with P prime being the conjugate exponent. And this is just related to the Hilbert inequality. In fact, the Hilbert inequality is this inequality. It's the same thing. It's just, this is the complete generalization of Hilbert inequality for all Banach spaces. Now, if we go back to Hilbert spaces, I mean, this of course works as well. But in the case of Hilbert space, you have the Cauchy-Schwarz inequality that everyone knows. But this one, okay, you can also, if you take the dual of the Hilbert space, so, which are called H prime here, then there is also this duality bound, which is the same as before, just given with Hilbert space norms. And this is in fact completely equivalent to the Cauchy-Schwarz inequality, and the mapping is given by the Riesz map. Oops. And in fact, what there is that so for any element in a Hilbert space, there's a unique conjugate that is called U star here, such that actually U with U star, and so this is the duality product, is actually equal to the inner product of U with itself. So that's the squared norm of H. Now, what is the important thing here? So what are the properties? So there's this Riesz map that tells us that actually this U star is R minus 1 of U, where R is the Riesz map. Now, just from this definition here, you see that the Hilbert conjugate preserves the norm. Now, if you reapply the Riesz map, you get back to where you started from. So if you do star followed by star, you have U again, and this is completely consistent with the reflexivity property, and also this star mapping. So Hilbert conjugate is also linear. So what's important here really is that we have two properties. First is the sharp duality bound. Here we're really like not having a smaller or equal here, but here having equality and isometry. And actually this brings us to a generalization. And this generalization was proposed by Berling and Livingstone, the notion of duality mapping. And it's just like making this stuff that is well known for Hilbert spaces, but also for Banach spaces. So if we have like a dual pair of Banach spaces, then you can consider two elements. So an element F in the Banach space, an element F star in the dual of the Banach space. And we will say they form a conjugate pair if we have exactly like before, we have non-preservation and a sharp duality bound. That here instead of inequality, we have equality. And so then we say that F star and F are Banach conjugates. And then if we fix ourselves a given F, then we can look at all the admissible duality, all the admissible conjugates of a given F, so which are called like F star here. And now the set of all those admissible conjugates defines the so-called duality mapping. And so it's well known that those guys always exist, so it's not empty. And now there are interesting cases where this duality mapping is single valued. For instance, when the space is strictly convex. In this case, actually, you do like with the Riesz, you can define an operator that maps a given guy into its conjugate, as given here. So here I will use like this straight J here as opposed to the slanted here, which defines the whole set. Now here's a photo of Arne Berling. It turns out that he was also the guy who helped to crack the code during Second World War, and so had very major impact, and is a great mathematician. Now, what are the properties of duality mapping? So first of all, I said that there's always at least one conjugate. Then there's also homogeneity. So if you have lambda f, you can pull out the lambda. For every f, okay, so there's a non-empty set, but this set of duality mapping is convex and weak closed. Now, the interesting part here is scenario is when is it single valued? It is single valued when the space is strictly convex. And actually, if the space is also reflexive, then in fact, there's a bijection, okay, so that's obtained with this duality mapping. And maybe here for reference, I just remind you that space is reflexive if you take the dual of the dual and you're back to where you started. And the strict convexity is also something we'll see a little further, but it's given by this definition here. Okay, so now is the thing about representative theorems. And I already told you we would like to have a more general representative theorem than the one that was used in machine learning. And I'm associating that to Lausanne Christmas 2018 because in the lab, I had a former PhD student, Julien Fajot, a very bright mathematician, and he would sometimes give presents to other students in the lab or myself as a theorem, okay? And since some of my students were working on those representative theorems, I decided, yeah, maybe I can give them a present. I will give them, maybe this mother of all representative theorems. And this is what I was doing on the day of Christmas. And my wife was not happy because I was supposed to pack presents, but I was still like trying to do my theorem. And I sent it to my students, in fact, on Christmas Day. Okay, so what about this mother of all representative theorem? In fact, this mother of all representative theorem, you'll see is amazingly sort of high level and looks kind of simple. So it's not, it's possible that it's well known, but I didn't really find it. So it could be hidden in some French math book or some Russian math book or German math book, but did not seem to be known in the form I'm presenting here. So the first thing, it just says, okay, if you look at this problem here, it has a solution, okay? That's not a big deal. Now, what's more interesting, it says that any solution is a x prime x conjugate of a common nu zero. And now the nu zero, okay, is in the span of those nu n. So let me remind you what are the nu n. So the nu n are the guys here. So it's the functionals that are acting on the function. Okay, and I'm saying here that you have a bunch of guys who should be linearly independent, and they should be part of the space X. Okay, so that tells us, in fact, that those nu here kind of specify the solution manifold. Okay, because there's a linear solution manifold here that is in the span of those guys. And then there's a nonlinear mapping, which is this duality mapping that will map that into the solution. Now, the cases of interest here is that if the Banach space is reflexive and strictly convex, then the solution is unique. And it's actually the duality map of this guy. Okay, so this will really define the solution manifold, which is of dimension m here, where m is the number of data points. Now, if X is a Hilbert space, then actually F0 is a linear combination of those nu star, and the nu star are just the Riesz map of those nus here. Okay, and so this really tells you that the solution lies in the one-dimensional manifold. No, m-dimensional manifold. Okay, this looks quite abstract, but remarkably, it's completely applicable and will give you many interesting examples of reproducing kernels. So first, let us go back to the old reproducing kernel Hilbert space case. So what is a reproducing kernel Hilbert space? There are many definitions, but there's a very simple one. It just says that the Diracs, so which are the point functionals, should live in the dual space. So that just means intuitively that the functions should be sufficiently smooth so that you can sample them. And then you have a reproducing kernel Hilbert space, and there's because a reproducing kernel Hilbert space is reflexive. So then we have a single Hilbert conjugate of this Diracs here. And then we're looking at the learning problem, which is given here. So it's as usual, you have your data term here, which is any convex, distance between the data point and the functions evaluated at the data points here. And with this regularization here. And what does our theorem tells us here? First of all, it's a special case because we can take x equal actually h prime here, which is the conjugate of the Hilbert space. X prime is h prime prime, which is actually equal to h because we're reflexive. Now the nu n here are just Diracs because we're taking samples at the data point. We have additive loss here, and the theorem then actually what we need here is just this conjugate mapping. And in that case, what's important here is R, which is the Riesz map that goes from H prime to H. And this is now a linear operator. I told you the Hilbert space is a space of function on RD. Therefore, you have the Schwarz kernel theorem. So and every linear operator is characterized by a kernel here. And in fact, the Hilbert conjugate here is just the kernel of this Riesz map. And then when I put that back together, oops. I'm going too fast. Here, I'm just getting the solution. Solution is in the linear span of those nu m star, and those guys here are just kernels. And so this is the traditional representative theorem of machine learning. Now, something very classical, but a little less well known. I mean, everyone uses Tikhonov regularization, but maybe not everyone knows that there's a very clean solution in continuous domain. In that case, H is a Hilbert space on RD. Again, we have this Riesz map that goes from H prime to H. We have now linear functions, not necessarily point measurements, but it could be MRI, or it could be whatever convolution where those guys are impulse responses, like a translation of the impulse responses. So now the goal is to recover a continuously defined function from RD to R, given some measurements here, which are like linear functions of the unknown function, plus some noise here. So then you frame the problem like that. So you're trying now to minimize the difference between the data points and here the simulated measurements on your function to be recovered, subject to a constraint here. And of course, here we're in the Hilbert space, so we're using the norm in the Hilbert space with some adjustable regularization factors. So now if you go back to the theorem, it's like before. We have like measurement functionals. There's just one constraint. The guy should be in the dual of the Hilbert space. Then, in fact, we define those phi m as being now the conjugate of those guys. And those, every guy has a unique conjugate. The psi here is now this convex function here. And then we know from the theorem that the solution should just be in the linear span of the phi m's. Now here, the phi m's are just the Riesz map of, the measurement functions. Now, once you know that, and that's again sort of mathematically magical, because we were solving a problem in infinite dimension, and here we know that the solution now lies in the finite dimensional space. So now we can just plug in this finite dimensional space, write down the problem as it is. That's just the optimal discretization. And then what you find is a so-called Gram matrix, which will be, the inner product between all those basis functions. And now the amazing thing, I would say, that's miraculous simplification. In that problem, if you do that particular discretization, it happens that the system matrix H is actually equal to the Gram matrix. And then that gives you a very nice closed form solution, which in fact is equal to that. That is well known, okay? But I mean, this is the sort of discrete solution that people will usually do when they do Tikhonov regularization. But what's maybe not so well known, that in the background, there's actually an optimal reconstruction in infinite dimensions. Okay, so let's get maybe something a little more modern, which is LP norm regularization. And this brings us to compressed sensing. And so there in compressed sensing, the goal, and first we start with finite dimensions. So the goal here is to recover an unknown signal from a set of corrected linear measurements. And so the linear measurements here are indicated with the scalar product here. So we're getting a bunch of measurements, like inner products with the unknown S plus noise. And if we're in the compressed sensing scenario, here we have less measurements than the dimension of our space. And so what's the strategy? Is to favor sparse solution. And so we can write the system matrix by just stacking up those H's. And then we want to solve that problem. Okay, so we have a data term and we are putting a penalty on the LP norm of the signal. And this is the sort of traditional formulation. And now what's not so well known is actually that you can get the closed form solution of the solution manifold. And how does that fit with the general representative theorem? Because even though we were in Rn, now here our space here is Rn equipped with a LQ norm, So that's now not a, this is a Banach space. And the dual is Rn equipped with the LP norm, and LP and LQ, their conjugate exponents. Then we have the Hölder inequality. Those norms are strictly convex if you are between 1 and infinite, not included. And then you have a unique solution. And then actually the duality map is also known. Okay, so this, and it's given by this expression here. And so that means that actually we have a parametric form of the solution here. So the solution now is parametrized in terms of a vector A here that lies in m dimension. Okay, so this is a nonlinear map, but that describes a parametric a manifold of the solution of our optimization problem. Okay, so relating this to the duality map is not completely standard, and in fact, it leads some interesting insights. and to look at the qualitative effect of Banach conjugation. So remember, I have this operation that gets the star, okay? Because we're having functions that live in our measurement space. And I told you, you need to take the Banach conjugate of those guys to actually span your solution. So here, okay, so this measurement space is the space LQ. And so here I have this Banach conjugation map. And now what I want to show you here in this graph is actually the Banach conjugates. And what I'm doing here, I'm just renormalizing. So the points, the blue points will always be the same, but I will renormalize them. And now I'm playing a movie to you. So now actually if I put 2, this is identity. Okay, so the blue and red points are the same. So now I just took a random set of blue points, and I'm now computing the red points, okay, for different P and Q. So I'm telling you the blue guys are always the same, they're just rescaled. Now what's interesting is the location of the red points. And so here we're going to P equal 1 and see what happens. Actually, all the guys, they go almost to 0, and there's a single guy that jumps out. It's actually the maximum. Let me play it again. So there's this sparsifying effect when I go to P equal 1. So maybe let me illustrate it here. So what is the qualitative effect of Banach conjugation? I mean, here the effect really is, there's no effect when we're in L2. Now the L infinite, I didn't discuss too much, but the L infinite here is just all the reds are either plus or minus 1. So it's kind of extreme, creates a saturation effect. And when I do for P equal 1, that it's very striking. You take almost anything and you do this Banach conjugation, at the end, it will produce something sparse. And this is actually the maximum points. Okay, that brings us to sparsity promoting regularization. And so the cases where the solution set is not unique. So in that case, the theorem says that we have a convex set, which maybe is not very informative, but we know that a convex set is characterized by its extreme points. And then here we have a very nice theorem that's actually due by Vincent and co-authors that tells us that in that case, the solution can be expressed as a linear combination of extreme points of the regularization balls. So that is the points in the Banach space whose norm is small or equal to 1. Now, what's an extreme point? So an extreme point is just a point that is any point that is not an interior point, any line segment lying inside of our convex set. I think it's better to take examples. And so if we look at L infinite, so this is from Wikipedia, just the illustration of the unit balls in the various norms. Now in L infinite, actually the extreme points are those red guys here, and the unit ball is this outer rectangle. So the extreme points are plus or minus 1, as I was showing you in my video on Banach conjugates. The other interesting case is L1, where the extreme points actually are sparse guys. So they're like Honecker guys. And now what about the others? Actually, I'm sorry for Vincent for your theorem, but it's not interesting for all the other guys because every point is an extreme point. Every guy on the on the outer on the boundary of the unit on the unit norm. But in that case, anyway, we know that the solution is unique with the complete characterization with the theorem. Okay, geometry of L2 versus L1. I think this people know, but it's just a contrasting L2 and L1. So for example, here we have the L2 ball, the L1 norm. If you look at the solution and doing this, so here you have a slab and you will have like, you will inflate the circle until it touches. So here you're in the case of L2. This is a unique solution. And L1, there's in this case, a unique solution and it's sparse, but what people don't show you when the solution is not unique. Okay, but now, good news. The two extreme points are still sparse, not the others. Okay, so that brings me now to new stuff. It's really what I wanted to tell you about sparse kernel expansions. Now here's Laurent Schwartz, because we need actually the formalism of distribution theory. So we have S, which is the space of smooth and rapidly decaying function. S prime is the space of tempered distribution. And we need a regularization operator that goes from S prime to S prime. So typical like Laplace, okay? Or no, not Laplace. Well, like yeah, I mean, Laplace goes from S prime to S prime. Now we will define what I call a native space here, which will involve the M norm, which is the total variation norm, which I'll tell you a little about in a while. And in fact, we don't need any operator here. We need an operator that's invertible. And now the inverse of the operator then has a kernel, a Schwarz kernel. That's very important in the theory. So actually every operator has a kernel, okay? So the thing that's maybe not obvious is you need an invertible operator, but if there is an invertible operator, it has a kernel. Okay, so now we have this space that I just defined. There's an isometry with the space of Radon measures. So what are the Radon measures, bounded Radon measures? Is actually the subset of distribution that for which this norm here is finite. And in some sense, this is the dual of the L infinite norm. So it's somehow L1, but it's a little more than L1. Okay, and it's really defined here by duality. So we are putting L infinite norm, but here the phi is a member of a Schwarz space. And then if we use this particular norm, and this operator here goes from ML to M, okay, so that's just the way it was defined here. And I told you the operator, we make the hypothesis that it's invertible, so then we can go from M back to where we came, and we have a kernel here. So that means that we can now map the extreme points of M. And now what's very interesting, and I think Vincent knows this very well, Vincent Duval and co-authors, that the extreme point of the space of measures, bounded measures, are actually Dirac's, plus or minus. So I can, in fact, map those Diracs via the inverse operator and get these guys here. Okay, so it's Diracs at any position. And then this allows me now to apply the theorem that just tells me that if I'm trying to minimize this, so it's machine learning, but instead of putting a L2 norm, I'm putting a M norm. It's almost the same as traditional, but not quite. And so the theorem then tells me that, in fact, F0 can be represented as a sum here of H's, so which are extreme points. But what is new now? In traditional framework, those guys, they lie on the data points. Now those guys don't lie on the data points. And the other thing is also those guys are fewer than the number of data points. Now the other very nice thing is actually the norm here that I'm using for regularization is equal to the L1 norm of the coefficient. In fact, this makes you a very nice link with L1 optimization. So then we can go to the translation-invariant case. In this case is where we use an operator that has a frequency response. And so then this means the operator as well as the inverse can be characterized by a convolution. And that means that the kernel then, instead of depending on x and tau like that, it actually only depends on the difference of those two variables. And then I can, for example, if I give myself the operator, I can determine the kernel by just doing this inverse Fourier transform, or vice versa. If I'm doing reverse engineering, if you give me the kernel, I can determine the operator by taking 1 over, if this thing is well defined. And in fact, I know, and this is from Schwarz theory of distribution, that I have an operator that goes from S prime to S prime, if and only if my frequency response is smooth and slowly growing. That's the only condition. And then examples of admissible kernels here are those guys which are like Gaussian-like functions. Oops. And maybe here, just to contrast, this is the classical solution where people require positive kernels that are fixed on the data point versus the new solution here, which involves the M norm, where you also have kernels, but it's more general, not just positive definite. I mean, it can be much more general, and the kernels are located at positions that are not necessarily the data points, and there are less kernels here than data points. Okay, but I wanted to end with neural network. So I actually, can I have like 3 more minutes? Yeah, okay. Deep neural networks. So you would say, what does this have to do in my talk? So you all know what's a deep neural network. Essentially, a deep neural network for mathematician, maybe I like to put it like that, is just a sort of concatenation of linear transformations followed by nonlinear transformation, which are pointwise followed by linear, nonlinear, linear, nonlinear, like written here. So you have linear steps, and maybe I'm indexing my layers by L. So I have lots of layers indexed by L. And for every layer, I have some neurons, which are now indexed by N. Now, going from one layer to the next, I'm using a linear, actually an affine transformation. And at every neuron, I'm just applying a pointwise nonlinearity. And usually I'm learning the linear part. Now let's get a little crazy, okay, or creative. What about learning the neurons? Okay, because who told you we have to use sigmoids or ReLUs? Now let's allow us to learn the neurons. Okay, so it's now almost the same as before. We are learning the linearities, learning the neurons. You say, yes, but this is crazy because there are too many parameters. Okay, so we need to use regularization. So we want to simple solution. No, we don't want to penalize simple solution like linear scaling. We want to be differentiable so that we can use backpropagation. And we want to favor simplest continuous piecewise linear solution with sparse derivatives. So therefore, now that's the link with what I was just saying. This is the right regularization. Okay, so the right regularization here is the second total variation. So it would be the M norm, oops, sorry, the M norm of the second derivative. That's still like defined by duality like this. And so here I have the native space for every neuron. So it's BV2. So it's the space such that the second derivative of those functions has a finite M norm. And then here's the represented theorem for deep neural networks. So now I'm trying to optimize all this. So it's complicated. I'm optimizing linear weights. I want to optimize neurons. And so to optimize the neurons, I'm just using a standard regularization. And on top of it, I'm putting the sum of total variation for every neuron. And what is the solution? The solution, if this thing has a solution, if it exists, what it tells us that every neuron actually has this form here. And so every neuron has a linear combination here of ReLU functions. And actually this, for people who know spline theory, you know this is a representation of a piecewise linear function with some knots. And so what does it tell us? It tells us that the optimal neural network has spline activation. So every neuron should be a linear spline. Now, the good news, it's completely backwards compatible, because if I just put one knot, okay, so the theorem says there are many knots. It doesn't tell you how many, just say less than data points. So if you just put one knot, you obtain exactly the famous ReLU neural network that everyone uses. Now, if you put your lambda going to infinite, you have 0 knots, and then you just find linear regression. So it's the grandfather of machine learning. And in between, we have like parametric ReLU. So that's a method that has been proposed in the literature, adaptive piecewise linear neural network also. So we're compatible with what's in the literature, but we have here a theorem that will justify all this. So why does that work? It brings us back to something really simple. Do you know how to interpolate those points? There's a classical solution, reproducing Kernel Hilbert space. So you put a Sobolev space, that's the classical solution. Now, what's the sparse solution? It's the one I just described in the theorem. You put total variation 2. And see here, you only get one knot. And you go straight go through all the data points. So it's much less obvious. But that's a sparse solution. Okay, conclusion. I presented to you a unifying results that supports all known representative theorems, at least a good subset of them. It's compatible with classical methods based on quadratic minimization. It also supports optimization in reflexive, strictly convex Banach space, and there's also quite some literature on LP splines reproducing kernel Banach spaces, and also modern sparsity, which involve now those sparse solutions. Okay, and it's remarkable for the generality because the theorem opens up new perspective. And what are the ingredients so that you can apply the theorem? You need actually Banach space. And you need the knowledge of the duality mapping versus extreme points. And also, what's remarkable in the proof of the theorem is relatively simple. It doesn't require Frechet derivatives. It doesn't require subgradients. It's just saturation of an inequality. But there are many open challenges, because now with the sparse representation, you don't know where to put the kernels. So you need to define algorithms that will locate the kernels. Also for the neural network, you need to determine how many nodes there are per neuron. And this brings me to the end. So I have to acknowledge participation of many people. They used to be confined as well, not, I mean, a little less so. Also, European Research Council twice. And here are some references here. And in particular, this paper here, which is more or less the talk that I gave. And for those who want details on the deep neural network, there's also a paper in Journal of Machine Learning Research. Okay, so thank you very much.